In note 6.7, example 4, we're going to write an equation to model the motion of a satellite that's fired into orbit. And the equation is going to give us the distance north and south of the satellite from the equator. So I'm going to read the description so we know what we're dealing with. When a spaceship is fired into orbit from a site such as Cape Canaveral, which is not on the equator, it goes into an orbit that takes it alternately north and south of the equator. Its distance from the equator is approximately a sinusoidal function. That means a sine or cosine function. Suppose that a spaceship is fired into orbit from Cape Canaveral 10 minutes after it leaves the Cape, it reaches its farthest distance north of the equator, which is 4,000 kilometers. Half a cycle later, it reaches its farthest distance south of the equator on the other side of the Earth, also 4,000 kilometers to the south. The spaceship completes an orbit once every 90 minutes. Let y be the number of kilometers the spaceship is north of the equator. You may consider distances south of the equator to be negative. Let t be the number of minutes that have elapsed since liftoff. And part A asks us to sketch a complete cycle of the graph of y in kilometers versus t in minutes. So I'm going to make a little axis here. So this is time in minutes, and this is distance in kilometers. And we're told that the maximum distance is 4,000 kilometers to the north. So this is kilometers north, I guess, would be. So 4,000 north. And on the other side of the Earth, it reaches a distance that is 4,000 kilometers to the south. So we're going to call that negative 4,000. Okay, and that's taking account the maximum and minimum values for this equation. Then we need to figure out the entire equation. So let's see what other information we're given. We're told that it completes an orbit every 90 minutes. So we know that the amplitude is 4,000, right? I already sketched the maximum and minimum. The period is 90 minutes. That's how long it takes to complete one orbit. So we're going to have key points every quarter period. So that'll be 90 over 4, or 22.5 minutes. That's going to help us set the scale for our x-axis. Then I'm not going to, well, let's see. We have a little more information here. We know that 10 minutes after it leaves the Cape, it reaches its farthest distance north. So we actually have a point that we can plot. So I'm going to plot that. So at 10 minutes, it reaches a point that's 4,000 kilometers north. I'm going to put a scale on the x-axis. So that's 10. And now, for convenience, I want to make my tick marks every quarter period from there. So from 10, I'm going to count by 22.5 minutes. So I'm going to have a point at 32.5. Adding 22.5 to that is going to put me at 55. Adding another 22.5 will put me at 77.5. And another 22.5 will put me at 100. That will be the end of one cycle. And now I know that something that's following a sine or cosine function will have key points every quarter period. So I was at 10, 4,000, then at 32.5 minutes, we're going to be at the equator, or 0. At 55, it'll be at the minimum, negative 4,000. At 77.5, it'll be back to the midline. And at 100, it'll be back to the maximum, which is 4,000. And then we can connect these with a nice smooth curve. And that is the function that we want to write the equation for. Okay, so we've done the sketch. Let's go to letter B. Letter B says, write the sinusoidal equation expressing y in terms of time t. And is it easier to write a sine or cosine first? I don't think either one of these is really much easier. Let's do the cosine first. To write a cosine function, let's choose a maximum value. So for cosine, I'm choosing the point 10, 4,000, and that means this function is shifted right. So this is shifted right 10 units. So this is right 10 for a cosine. And since we chose a maximum, it's not reflected in the x-axis. So we won't have a negative cosine function. And we know the amplitude is 4,000, so A is 4,000. We don't know the value for B, so let's figure that out. We know that the period, I'll do that up here, the period was 90 minutes, so the period equals 90, which is going to be 2 pi over B. So I'll multiply both sides of the equation by B. And then I will divide both sides of the equation by 90. So that B is equal to pi over 45. So we know A, we know B. There is no vertical shift. The axis of oscillation for this graph, so let's see, the axis of oscillation is at y equals 0, so D is equal to 0. So we know our values for A, B, and D. Those will be the same for both the sine and cosine. I already chose the information for cosine, so let's go ahead and write the equation for cosine. So we're going to have y is equal to the amplitude, 4,000 cosine, and then B is pi over 45. But then we want to have B factored out, so we're going to say T minus 10 because this function is shifted right 10 units. D is 0, so that's all that we need to write for the cosine function. And let's write the sine function. So if we're thinking about sine, we need to pick a point where the graph crosses through the axis of oscillation. I can choose this point, which is right 32.5. So if I choose this, right 32.5, but my function is decreasing as it crosses the axis of oscillation. So this will be reflected in the x-axis. So it'll be a negative sine function. So we're ready to write the sine equation. So we're going to have y equals 4,000, that's the amplitude, times sine. Pi over 45, the B value is still going to be factored out. We're going to have T minus 32.5 because it's shifted right 32.5 units. D is still 0. And I forgot, it's a negative 4,000 sine. If you had chosen the value at 77.50 for sine, then it would not be reflected. So an alternative sine function would be positive 4,000 sine of pi over 45 t minus 77.5. That's another function we could have written. Letter C says, use your equation to predict the distance of the spaceship from the equator when t equals 41 minutes. So all we need to do is substitute t equal 41 into one of our equations. I'll use the cosine equation. So we have y is equal to 4,000 cosine pi over 45 times 41 minus 10. That's what t is. And I can simplify it a bit. So this will be 4,000 cosine pi over 45 times 31. And this you'll need to enter into a calculator. And if you do so, you'll get negative 2236.7 kilometers. And we would answer this. This is really, or 2236.7 kilometers south of the equator.